Guys, welcome back to my YouTube channel. For today's episode, we will be having experiment number 5, or our half-wave rectifier circuit with RC load. For our objectives, we aim to simulate the half-wave rectifier with RC load using PSpice software. Second, we aim to utilize the software to observe the behavior of half-wave rectifier with RC load, with the resistor and capacitor load. And third is to determine various quantities using PSpice software. So we will be considering, this circuit here on this figure, and with this, let's just zoom this in. So we can see that we have here a parallel capacitor, and a parallel resistor load. Notably, this capacitor serves as a regulatory for our output voltage, which is one of the uses or function of certain filters, and this resistor here serves as our circuit load. So now understanding rectifier circuits, like this, for example, our half-wave rectifier with RC load. Rectifier circuits aim to convert AC voltage to DC voltage as our output. So here, the capacitor serves as our limiter, or let's say it controls or regulates the variation of the voltage, and it is important in our rectifier, or it serves as our filter, and this resistor serves as our load. So in this experiment, we will be constructing a half-wave rectifier with RC load, and we will set the value for our resistor to 2 ohms. Our capacitor will be 100 microfarads, and we will use Phi sign as our voltage source, and deep break for our diode. Our AC source will be 220 VRMS, and we will be converting this to V amplitude by multiplying it by square root of 2. And our frequency will be 60 Hz. In the simulation settings, we will choose time domain transient for our analysis type, and we will set the runtime to 16.67 milliseconds, and when we convert it to frequency, it will be 60 Hz, just like here on the given, for one period of the source. And for our forward instruction, we will set the maximum step size to 10 microseconds to get an enough sampling of our waveform. And fifth, we will perform transient analyses and complete the table 1 and 2 below here. So as you can see here, we will get, we will get these values, which is our theta here, angle theta, our V out max, V out mean, our change in delta VO, delta V out, our current peaks, current on our diode, on our capacitor, and this one here. So now we will be constructing our circuit. So now here is our circuit. We already placed our components here. We place a V sign, voltage source, a diode, a D brick as our diode, and a capacitor here, and our resistor. So for our V amplitude, we are given 240 as far as I can remember, or let's check here. We are given 220, I guess. We are given 220 VRMS, multiply it by square root of 2, we will be having 311.127 V amplitude. So let's click OK. Our frequency will be 60 Hz. So let's click it here. Let's just move this one. Our V off is typically 0, and our AC is 0, and our capacitor has a value of 100 microfarad, 100 microfarad, and we have here our capacitor is, our resistor is 200 ohms. So now we will be connecting our circuit here. Let's just connect it through a wire here, and then the capacitor is in parallel with our circuit, and then let's connect this one here. Let's connect this one here, and then this one. And do not forget to put a ground, 0 cap sim on our circuit here on this. Here on this voltage source. Let's click escape and then click ground here. And this will be our circuit, as you can see, and we will create a new simulation profile later on. So now we have to create a simulation profile, new simulation. Let's rename this RC circuit. And then let's click create, and then here we will be having a pop-up which will allow us to edit our simulation settings. So we will be using our runtime to we will be using 16.67 milliseconds as our runtime, and our start and our maximum step size will be 10 microseconds. So 10 microseconds, just to correct. So we will be clicking apply and then click OK. And then here on our Word file, we are asked to fill this table, okay, table 1, which will allow us to record the results for our theta and for our voltage max and voltage min and our delta voltage out, okay, and the current and the peak currents here. So we will be going to our simulation and we will be running this one, okay. So let's wait for the pop-up. So let's go here. So let's put a voltage probe here just to make sure that the circuit will be working correctly. And let's run the PSpice again. So let's go here. Okay, so as you can see, so to get our angle theta here, so as you can see on the graph, this is our output voltage waveform, okay? To get our angle theta here, okay, required by our table, we will be adding a trace, okay, which is our input voltage. So our input voltage is V2 lost, okay? This red graph here, or waveform, is our input voltage. So to get our angle, we will measure the point here wherein our input voltage and our output voltage intersects, okay, or it meets. So first, to set our settings to degrees, okay, we should click here axis settings and then axis variable. Then we should multiply time times 60, okay, and times 360 to make it degrees. So let's click OK. Let's click OK here. So let's toggle cursor and let's measure our intersection here. So let's just zoom in first, okay, that's fine. So now after turning on our cursor, let's move it here where our input and output voltage intersects. Okay, so I guess this is a point. Okay, let's move it a little here where they intersect. So as you can see, okay, as you can see, here is the intersection of our input and output voltage, which gives us, okay, I guess here, which gives us a value of x as our x is equals to 102. Okay, and y is equals to 240. So our theta or our degrees is 102. So you can see it here. So x is equals to 102 and y is equals to 240. So now, putting our degrees here or our value for theta, we will be having 102 degrees. So now let's get our voltage max. Okay, our output voltage max. So let's just delete this one here, and let's toggle our cursor, or let's move our cursor for the peak value of our voltage. So as you can see here, our peak value for our voltage is 310.087. So let's encode it in our paper here. Okay, let's just... So our output voltage max is 310.087 volts. So let's go to our simulation again, and we will be measuring the output voltage minimum. So as you can see here, our output voltage minimum is 167.571 volts. So now measuring our average output voltage or our delta VO here, let's go to our simulation and then let's add trace. Then let's click here average and then let's find for the voltage across our R. Okay, as far as I can remember, it's R1. So let's find it here. So again, for our average output voltage, let's add trace and then average. And then we will be clicking voltage R1, 2. So let's click OK. As you can see, I already edit the axis settings here. Okay, our axis variable. I already removed the times 60 and times 360 for it to be back to normal, which is our time. So let's toggle our cursor and let's move it here on the end of the waveform for our average output voltage. So our average output voltage is 223. Okay, as far as 223.664. So here our average voltage is 223.664 volts. So now let's measure the peak currents from the diode and from our capacitor. So again, we will be adding traces. So we first measure the peak diode current. So it's ID1. So let's click OK. Okay. So cursor on, and we should measure the peak of the output waveform. So as you can see, our peak diode current is... So as you can see here, as we move our cursor, okay, our peak diode current here, as we move our cursor is, okay, let's move it a little here and then here, is 11.817, oh, it's 26, well, 11.800, this one, 11.826 amperes. So let's record that one for our peak diode current. So We already measured the peak diode current. Let's measure the peak capacitor current. So now for the peak capacitor current, let's delete this one and then let's add another trace. So IC1. So let's click this one, then let's click OK. So let's have our cursor on and let's move our cursor. Okay, so as you can see, our peak capacitor current is 11.717 amperes. So as you can see here, we already completed our table 1 quantity and our table 1 results. So now we will be measuring our we'll be getting our measurements for table 2. So now continuing with our simulation, we will be fulfilling our table number 2 here. So we will be getting the average diode current, the RMS capacitor current, the average, okay, rather we will be getting the average power across R1, the average power across our voltage supply, and our average power across the diode. So we will be getting, we will be getting here, we will be getting those values here in our simulation. So for our first value, we will be getting the average current across the diode. So let's add this trace, then average, and then ID1 here. So let's click OK. So as you can see, this is our average, this is our output waveform for our average current across our diode. So as you can see, our average current is 2.1239 amperes. So that's our average current across our diode. So now recording the average current across our diode, we have here 1239, okay, 1239 amperes. So next is the RMS current across our capacitor. So let's delete this one. Okay, delete. So let's add some trace. So RMS current. So we will be using RMS here, RMS. So RMS, oh, sorry, let me delete that. So RMS and then IC1. So IC1 here, okay. So measuring the RMS current across the capacitor. So now let's turn on our cursor and then let's measure it here on the end of the waveform. So our RMS current across the capacitor is 4.2535. So let me record it. So recording our RMS current across the capacitor, we have here 4.2535. So next is the average power across R1. So let's go back to our simulation and then let's add our, so let's add another trace and then we will be measuring the average power across our resistor. So average power across our R1. So just like what we were doing a while ago, let's measure the average power here on the end of our waveform. So as you can see, our average power is 269.457 watts. So recording our average power across R1, we have here 269.57 watts. So we will be recording next our average power across our voltage source. So let's go to our simulation. So let's delete this one. So let's add another trace and then average, and then we shall find here WV, okay, WV2 here. So, okay, so this is our average power across our voltage source. So as far as I can remember, it's a V2. So let's go here and then let's toggle our cursor. Then let's measure our average power across our voltage supply. So we have here, and our average power is negative 357.608 watts across our voltage supply. So now recording our average power across our voltage source, we have here negative 357.608 watts. So lastly, we will be recording or measuring our average power across our diode. So let's go here, then let's delete this one. Okay, let's delete this one. Let's add trace. So average power across our diode. So WD1 here. So that one, and let's toggle our cursor and then let's measure our power here on the end of our output waveform. So as you can see, we have here our value for our average power across our diode, which is 3.9197 watts. So let me record it. Okay, so now concluding our experiment, we have here our results for table 1 and our results for table 2. So as you can see, as you can notice in our experiment, we only measure the parameters using our first period of our output waveforms, okay, considering that our period is 16.67 milliseconds in accordance to our, frequency here, which is 60 hertz. And if you can notice, our values of current as well as the values of our voltages here are quite large or big as what we expected, because we only restricted the data at the first period of our output waveforms. But if we will be considering the steady state, okay, the steady state results of this waveform, okay, if we will be considering editing the simulation, and considering a 50 milliseconds runtime, Okay, so let's click OK here. And if you will be adding another trace, okay, which is the average, let's say the average current across our diode here, or let's say the current, okay, the current across our diode. So let's click our current here on the diode. Okay, so notably, when we set our simulation settings for in our runtime is 50 milliseconds compared to 16.67 milliseconds, as you can see here on this output waveform, which is just the first period, it matched our peak current of our diode, which is, as far as I can remember, it's 11.826 amperes, okay, as you can see here. But if you will be considering the steady state values of our currents and our voltage, you can significantly notice that the steady state values or parameters are smaller in values compared to our first period values. So if you want a more reliant, or more reliable or accurate result, you can consider setting our runtime to 50 milliseconds in order to get, let's say, at least 3 periods, a minimum of 3 periods, to measure the steady state values of these parameters. But to satisfy this experiment, we will just be using the first period, okay? So that's our experiment number 5, okay? So I hope you learned something, and we will be discussing our results, okay, and our realizations on our conclusion. Now, as our conclusion, first, employing the ORCAD PSpice program, the notion of using an RC load and half-wave rectifier circuits was met and simulated. The angle in this sort of circuit was discovered to be at the point where the input AC voltage and output voltage waveforms intersect. The maximum output voltage in this circuit was 310.087 volts, while the minimum output voltage was 167.571 volts. And lastly, as a result of the large variation in output voltage, it was determined through the experiment that the capacitor value was not advisable in a filter. There should be less volatility or changes in output voltage levels for a capacitor filter to be efficient. So that's our experiment number 5. Again, my name is Rica Casabuena. I hope you learned something from our experiment today, and I hope I will be seeing you on our next class. Bye for now!